If you've read a sci-fi novel, watched a cartoon, or scrolled through a webcomic in the last 50 years, you've likely encountered Schrödinger's cat. The concept of a feline trapped in a box, somehow existing as both alive and dead at the exact same time, entered the mainstream consciousness in the 1970s, largely credited to writers like Ursula K. Le Guin. But the way we remember the cat today misses the creator's original intent. Erwin Schrödinger used the idea to highlight what he saw as a deep logical flaw in the physics of his time. To understand why he invented this bizarre scenario, you have to look at the fierce physics debates of the 1930s. Scientists were wrestling with the measurement problem, the deeply confusing question of how subatomic particles behave when they are not being actively observed. Schrödinger devised this thought experiment as a sarcastic joke. He used a common household pet to illustrate the absurdity of a theory that seemed to replace objective reality with mathematical probability. That theory was led by physicists Niels Bohr and Werner Heisenberg. Together, they championed the Copenhagen interpretation of quantum mechanics. This diagram illustrates their core concept, called superposition. The math suggested that unobserved quantum particles don't exist in a single defined state. Instead, they exist as a blur of multiple possibilities simultaneously. It is only when a measurement or observation is made that the system collapses and forces them into a definite reality. Not everyone accepted this indeterminate view of the universe. Albert Einstein pushed back aggressively, forming an intellectual alliance with Erwin Schrödinger to defend the idea that the world exists independently of our measurements. In their letters and the 1935 EPR paper, they argued that as particles remain a mathematical blur, even when separated by vast distances, then quantum mechanics is a limited, incomplete description of physical reality. To win the argument, Schrödinger realized he needed to take the microscopic math that Bohr and Heisenberg were defending and translate it into a macroscopic, everyday absurdity. Schrödinger laid out a thought experiment. He asked his colleagues to imagine a simple, completely sealed steel chamber, ensuring that no outside observer could possibly see what was happening inside. Inside this box, he placed a single atom of a radioactive substance. He set the parameters so over 1 hour, there was exactly a 50% probability the atom would decay and a 50% probability it would do nothing. Next, he connected this subatomic coin flip to the macroscopic world using a Geiger counter wired to an electrical relay switch. This is the lethal mechanism. If the Geiger counter detects a single decayed atom, the relay trips. It drops a tiny hammer, which shatters a glass flask of hydrocyanic acid and releases the gas. Finally, he placed the last subject in the chamber, the cat. A macroscopic biological life is now permanently tethered to the subatomic state of that single radioactive atom. Here is the trap he set. The Copenhagen interpretation dictates that until the box is opened and measured, the atom exists as decayed and undecayed. Therefore, the theory is forced to conclude that the animal must be both alive and dead until someone looks inside. Schrödinger employed this reductio ad absurdum to show that the existing view of quantum mechanics was, in his words, ridiculous. Rather than abandoning the theory, the physics community leaned into the paradox, searching for new ways to explain how such a state could exist. Defenders of the Copenhagen view maintained that the box, the poison, and the cat truly do form an inseparable, indeterminate blur. To them, the feline state remains unresolved until a human physically opens the chamber. This led physicists John von Neumann and Eugene Wigner to propose that the collapse of these multiple states requires a conscious observer. They argued that the physical chain of reactions only resolves into a single reality when it is processed by a human mind. Without a conscious observer, the entire system, the cat, the poison, and the box, remains in a state of superposition. In 1957, Hugh Everett offered a different explanation, introducing what we now call the Many-Worlds interpretation. This diagram shows Everett's model. Under Many-Worlds, the cat is both alive and dead, but the act of opening the box causes the universe to split into two distinct parallel realities. One version of the observer sees a live cat, and a separate parallel observer sees a dead one, with no interaction between the two. Schrödinger's sarcastic attempt to mock superposition failed to destroy the concept. Instead, it provided the framework physicists use to debate the fundamental nature of reality. In modern laboratories around the world, physicists are working to physically construct the systems Schrödinger once dismissed as impossible. Maintaining a superposition in a complex biological organism remains a massive technical challenge, as interaction with the environment, a process called decoherence, collapses these states almost instantly. To study this boundary, researchers are instead constructing simpler mesoscopic systems. Early proofs of concept achieved these cat states by trapping individual photons or suspending single beryllium ions in two states at once. Researchers then pushed the scale upward with experiments involving a superconducting quantum interference device, or SQUID. This diagram illustrates the SQUID results. Instead of a single atom, researchers moved billions of superconducting electrons en masse. When placed into a Schrödinger's cat state, this massive cluster of electrons moved in two completely opposite directions around the loop at the exact same time. More recently, a piezoelectric tuning fork made of 10 trillion atoms was placed into a superposition, where it was simultaneously vibrating and standing perfectly still. The blurred model that Schrödinger used to mock his peers has become a testable reality, expanding the scale of quantum effects from individual atoms toward macroscopic machines. Which brings us back to the original measurement problem from 1935. At what exact threshold of mass, time, or complexity does quantum weirdness finally collapse into the predictable, everyday reality we experience? Modern physics is still searching for this answer. Researchers are pushing cat states to larger and larger objects, looking for the specific point where the rules of the subatomic world stop applying to the world we can see and touch. A frustrated physicist's attempt to point out a flaw in quantum theory ended up defining the boundaries scientists now use to explore it.